So what's the catch, right? Pipelining is this beautiful thing that allows us to optimize the execution of all of our instructions and all the time, but it's really hard, right? It's much more complicated than single cycle machines or even multi-bus machines, and it leads to other problems that we're going to have to address. So besides the fact that it's a very complicated thing to build, we started with an assumption that instructions are the same and independent. And we know that that's just not true. So now we got to find out how to handle the fact that instructions aren't the same and aren't independent. So we identify what we call hazards. Hazards are things in our code that are going to sort of impact the operation of the pipeline, that they're going to get in the way of having things work properly. There are really three kinds of hazards: structural hazards, data hazards, and control hazards. And we'll talk about each of these things one at a time. Simple pipelines typically don't have structural hazards, but it's worth talking about them anyway. So what are they? Structural hazards are when there's a physical part of the machine that we didn't pipeline very well, where it might be needed by different components, by different chunks of an operation, right? So if there's some overlap between functionalities, we might find ourselves in a structural hazard where one instruction has to wait until another instruction is done with the resource. So that's one. Data hazard is where one instruction has to wait until another instruction has finished doing whatever math it is that will produce the data that the first instruction needs. So if you're doing instructions where you're adding two numbers together and then taking the result of that and comparing it to something else, this first one's got to finish before this next one can do its thing. And so these are data hazards, where the data is not ready when we need it. And then the third kind is control hazards, where we have to make a choice, right? And that choice might end up with us executing different instructions. If we're taking a branch or a jump, in any circumstance where we're changing the program counter, that change to the program counter won't be ready in time for us to fetch the next instruction. And so we have to either wait or we have to do something else. So these are those three kinds of hazards: structural, data, and control, where we have to wait until a piece of the hardware is ready, we have to wait until data is ready, or we have to wait until the new program counter is ready. So each one then in sequence. Structural hazards, again, we don't typically have structural hazards in small pipelines, and the one that we just built doesn't have any structural hazards. But we can find structural hazards emerge once we start to add things like superscalar, multiple issue, out of order execution. Structural hazards can reemerge, and so we have to be ready for them. What are the solutions? Well, we can schedule, stall, or duplicate. Schedule means that we choose to execute instructions in a different order to avoid that structural hazard, right? This instruction needs this resource, and this instruction is not done with it yet, so we'll just put that aside and do something else until this is finished, and then come back and do that thing that's waiting for it. Once we start executing instructions out of order, all sorts of other problems emerge that we'll talk about later. But this is one thing we can do, is the assembler can reorder execution to avoid these structural hazards. If we don't want to do that, we can just stall. We just wait, right? Wait for the instruction that's using the resource to finish before we issue the instruction that needs the resource. And that just, we just wait. It's kind of a waste, because there's all of the functional elements of the pipeline that aren't doing anything in that cycle or those cycles. But that's a solution to a structural hazard, is just wait until it's ready. Right? And then the third solution is to duplicate. If there is a functional component in the hardware that is causing delays because lots of people need it, let's just build a few of them. And then each instruction can be issued into the structural element that might be available at the time. And again, this is a superscalar thing that we'll talk about a little bit later on. Scheduling and stalling are things that the assembler can do. Duplicating is we have to do that at design time. We can't duplicate hardware after we have built the machine, of course. So what about data hazards? Here's an example, right? We're going to add R1 and R2 and put the result into R0. And then right away after that, we're going to add R4 to R0 and put the result in R3. The data in R0 will not be ready when the second instruction needs it, because it takes a few other cycles before the result is written back to the register file before it can be read as a source for the next instruction. Okay, so that's a data hazard. And again, we have a few possible solutions. Schedule, just like before, we can reorder instructions to wait until the things are ready. We can stall, just wait until the result is ready. That will solve any hazard, but it's a big waste of resources, and so we don't necessarily want to stall if we can avoid it. Then bypassing or forwarding is a technique where we can take the result from the ALU that we know we're going to need it in the next instruction, and instead of passing it along to finish off the instruction, we can right away bring it around into the input of the ALU as a source, right? Because we know we're going to need it, because we know that these instructions are happening one after the other. And so we bring that instruction result, the ALU result, back into the beginning of the ALU and then have it ready for the next instruction even before it's been written back. So this is called forwarding, data forwarding or data bypassing. It adds a lot of extra hardware and complexity, but it solves data hazard problems, or at least mitigates their impact. And then the last thing we can do, and this makes people nervous, but it's a reasonable technique, is speculation. We can just guess. If we think the result is likely to be 0 because of something, right? We're predicting the future. We can just operate as if that's the result. And then if we were wrong, we just go back and change it. I mean, it's no more of a waste than if we had just waited for the answer, right? If we can speculate the result instead of waiting for the answer, if we're right, then we get ahead of the game, right? We're a little bit faster. It's not exactly true to say that it's no extra effort, because often speculation doesn't just mean, like if we speculate incorrectly, it doesn't just mean we throw the thing away and start again. It means that we might have to like flush the entire pipeline because outcomes based on those values might have already been in play. And so speculation has the opportunity for increased performance, but if we get it wrong, we sometimes have to dig ourselves out of a hole. So that's solutions to data hazards. And then control hazards, similar to data hazards, we can stall. We can't really reschedule because we have to do one thing before we get the result, right? If we're going to be making a decision based on a result, we can't really reorder. We have to have that result. And so we can wait for that result with a stall, just like before. We can bypass or forward, just like before. We can get the result from the ALU and bring it back to the input of the ALU for the comparison or whatever. And we can speculate. Now, speculation in control hazards is where we get the idea of branch prediction, which is a big, important topic that we're going to spend a bit of time on. Very complicated, lots of stuff that can go wrong. But again, as you see, each time we add a feature to the hardware that makes our operations faster, we end up with circumstances that may be problematic, and we have to fix those. So advantage, disadvantage, advantage, disadvantage, and we keep adding complexity all the time. So those are the kind of things that can go wrong with pipelining and how to fix them.